Happy day and welcome everyone. Today what we're going to be talking about is spontaneity, but specifically when we're looking at batteries. So remember, when we say spontaneous now, we're actually changing it up. We're going to call it thermodynamically favored. But what does it mean anyway? Spontaneous reaction will proceed in the direction written, meaning your reactants will turn into products without the addition of any outside energy. It indicates nothing about the time that the reaction is going to take. We know that the free energy change, delta G, measures spontaneity, but we also have a couple other things that we can relate to spontaneity, and that's kind of what we're going to be talking about and showing today. So one of the things is, remember, Sarah eats gross ham. So if we have Sarah eats, we want both of these to be positive, and gross ham, negative, negative. Do not forget that Sarah, positive delta S, and a negative delta H separately do not indicate whether you have a spontaneous reaction or not. So those need to be tied together, but a negative delta G does, and so does a positive E cell. So when you have a reduction in oxidation and you take a look at your E cell value, then if it's positive, then we know that that's favored. And there's one more thing, so let's write these down. We know that if it's thermodynamically favored, we want our delta G to be negative. So in other words, we have free energy that's available, so we want that to be negative. We do want our E cell to be a positive value. In addition to that, what also relates directly is K, our equilibrium constant. And we know that if we're favoring the products, meaning that our reaction's moving in the direction from reactants to products, K is greater than 1, and if K is greater than 1, we have more products than reactants at equilibrium, then that means that it's also a spontaneous reaction, or thermodynamically favored. So all three of those, and it's really important to remember that all three of those are going to basically give us a spontaneous or thermodynamically favored reaction. Okay, so we already said when delta G is negative, the reaction is spontaneous. Also a positive EMF is spontaneous. There's a relationship that we have. So we take a look at this equation, and the equation is delta G is equal to negative NFE. Now delta G we know is our free energy, and typically our free energy is going to be measured in kilojoules, or depending on kilojoules or kilojoules per mole. N is our mole of electrons transferred. And when we say this, we're basically looking at our LCM, our least common multiple between the two. And don't forget that if you're using cells, that even if you multiply by 2 or you multiply by 3, that doesn't actually change your voltage. So your voltage will remain constant. And Faraday's constant will be given to you on an equation sheet. So let's take a look at an equation sheet here. If we scroll down to the thermoelectro section, we can see right here Faraday's constant, 96,485 coulombs per mole of electrons. Right, so let's write that down. So 96,485 coulombs per mole of electrons. And when we say mole of electrons, we're talking about the electrons that are being transferred. Okay, that's going to be really important too when you end up doing electroplating or metal plating problems. Okay, so note, Faraday's constant is in coulombs, and a coulomb is a joule per volt. So actually, our G is going to be in joules, not in kilojoules. So according to this equation, as long as this is in moles of electrons, that's our moles of electrons, this, our Faraday's constant, is in coulombs per mole of electrons, and our E is going to be in volts. But like we said, a volt is actually, if we were to do our algebra out, it's a joule per coulomb. So that's what a volt is. And if we cancel things out, then our mole of electrons cancels, our coulombs cancel, and what we end up being left with is actually joules. So always be careful with your units. So if you are using Faraday's constant, then make sure that you remember that that would actually be in joules. Okay. So if your N and your F are always positive because there is no negative for Faraday's constant and no negative for moles of electrons, it's always going to be a positive number, then what should your sign of delta G be? Well, it always has to be negative in that situation because it's a negative NFE. So keeping that in mind. Now, if your N and F are positive and your E ends up being negative, then two negatives are actually going to make a positive. So if I have in other words, change the color here. If I had, I'm talking about this way, if I said my N was positive, my F is positive, and in this case, my E, let's say, is negative, well, I've got a negative times a negative, and like I said, a negative times a negative is going to give you a positive delta G in that case. And a positive delta G would mean that your reaction is non-spontaneous. Okay, so before we actually take a look at this question, I do want to reference real quick here what the differences between a voltaic cell and an electrolytic cell, and also sometimes they'll change up the notation, and so I want to make sure that you're aware of that. So you'll see that there may be this type of notation down here where they actually give you this like double bar and these single bars. And so the way that they're writing this out is in the order that we know, anox towards your red cat, so the way that the electrons are going to move. So we do have our anode on this side and our cathode on the other side. But what they do is they split it up so that they have this little tiny bar here, and that's indicating the solution that it's in. But what's important is that the solid anode and cathode are actually at the ends. And so this would be my anode. This would be my cathode at the end. This here is actually representing the salt bridge. And that's a really important part. And remember, the salt bridge is there to maintain electrical neutrality, so keep that in mind. So I wanted to show you that notation real quick, just in case you see something like that. And the other thing I wanted to show you was, what if it's electrolysis? And electrolysis is different from a voltaic cell, because in a voltaic cell, what ends up happening is you have your negative anode, anox, and you have your positive cathode, your red cat. In an electrolytic cell, it's actually reversed. So you put a battery in, and now it's going to go against what nature wants to do. So instead, your anode is actually positive and your cathode is negative. And I did kind of want to show you this just because it's kind of cool to see how the electrolysis of water works. Actually, because our full reaction is water turning into hydrogen and oxygen gas, but we know, yes, there's hydrogen and oxygen gas that can be produced at those different electrodes. And so which one happens where? I do have an easy way of remembering it. I always say that oxygen is produced where oxidation is happening. And so oxygen is produced at anox, whereas your red cat is where your hydrogen is going to get produced. So I just have an easy way of remembering that. But you can see here, now we would actually, because this is 2 electrons and this is 4 electrons, we would actually have to multiply this entire reaction by 2. So this one would have to be double, but remember, your voltage wouldn't change in that matter. But then you can cancel out and you can see how everything ends up adding up, because we've got the 4H plus here instead of the 2, and this becomes 4 electrons, and this becomes 2H2. And so you can see that the 4 electrons cancel out with the 4 electrons, and the 4H plus cancel out with the 4H plus, and we're left with our overall reaction, which is what we know to be the water reaction. So just kind of cool to see that the reduction actually happens. It's the negatives and the positives are just switched, just because our battery is the one that is pushing that in the opposite direction. So I also wanted to show you, this question is kind of interesting because it kind of puts a little bit of a spin on how we would work out problems. This is saying, it's asking us if the reaction is spontaneous or not, okay? So it's not telling us to write the spontaneous reaction, because what we would want to do is we would want to flip the lower voltage, since both of these are reductions. How do I know? Because I can see that there's 5 electrons on this side and 2 electrons on that side. My electrons are on my reactant side, meaning that the reaction's gaining electrons. GR means that these are both being reduced. One of them needs to be my oxidation site. So what I'm going to do is I'm actually going to use a little bit of that circle, square, triangle from Hess's law that we do, and I'm going to see if I can find what side it's on and which one needs to get flipped. Well, very quickly, I see right away that the IO3 minus is on the wrong side. This one needs to get reversed. And if I reverse that, and remember, it doesn't matter if I multiply by 2 or divide by 2, the question is just asking me if it's spontaneous or not. That means that it's a negative 1.195 volts. Keep this one the same then, because, so this one must be my reduction. So this is going to be my oxidation, and this one must be my reduction. The one that you're keeping the same is your reduction. And so this is a positive 0.337 volts. And when you add those together to get your cell voltage, we get a negative 0.858 volts, which means it is non-spontaneous. So remember, this is our E cell. You want your E cell to be positive in order to have a thermodynamically favored reaction. Okay, so just wanted to show you a little bit of that. All right, voltage and equilibrium in the Nernst equation. Okay, so the Nernst equation, they took off the equation sheet and then they put it back on. So let me show you where the Nernst equation is. So if we take a look down on the bottom here, here it is. It's E cell, the cell's voltage, is equal to E cell standard condition. So if you already know what the standard conditions are, minus R times our temperature, Kelvin, moles, Faraday's constant, and then ln of Q. Now, Q we know is random concentration. So anytime that you have random concentrations, you're going to end up using Q. It wasn't necessarily that they wanted you to be able to do the math on this. It was the fact that they put the equation back on because they wanted you to conceptualize it. And so that's really important that we understand that before we look at the Nernst equation. Okay, so it says the standard EMF is related to the equilibrium constant and Le Chat's principle will still apply. Remember, Le Chat's principle says when you add to one side, it shifts the opposite side. When you take something away, put it back. Okay, so just keeping that in mind. It says the standard EMF generated by a cell increases as your equilibrium constant increases, which makes sense because when we say the equilibrium constant, we're talking about K, and K is equal to the concentration of our products over the concentration of our reactants. And if our reaction is moving forward, making more products, then our products should increase as our reactants decrease, so then our K should end up getting bigger. Now, we're not actually saying that K, whether K is greater than 1 or not, we're just saying that our K should increase as we make more products, and that's going to be really important, okay? So this means if K increases, then you're favoring your products more. So the concentration of your products are going to increase, and obviously your reactants decrease. So then your E cell should actually go up as well. So when your K goes up, your E cell, your cell potential should go up, meaning you're favoring the products. It's important to note the difference between K and Q. We already talked about this. K is when you're already at equilibrium. Your reaction has come to a point where there is no net change. Whereas when you're at Q, then Q you want to compare to K and you want to reach equilibrium. So sometimes you passed it and you have too many products and you want to come back. And so it could go either way. Okay, so if Q is less than K, the reaction is going to favor the products. We're going to move in the forward direction. That means that your E cell should increase. We're going to be making more products, okay? So if we have reactants and products, our reaction should be going in this direction toward our products. If Q is too big, then our reaction needs to go backwards. And so if we have reactants, arrow, products, our reaction should actually be going backwards, and that means our cell potential is actually going to go down. So your E cell might start off as a 0.13 and go down to like a 0.10, but it's not going to change by that much, okay? And so this is where the conceptual piece versus the mathematical piece comes in. How much does it change by? Okay, so here's our Nernst equation. We have our equation, we have our R value, we have our moles of electrons, we have our Kelvin, we have our Faraday's constant. Don't forget that a Coulomb is actually going to be a joule per volt, which means that we want to make sure that we're using the 8.31 value, which is in joules, okay? So keep that in mind here because a joule is a volt times a Coulomb. So we're not necessarily going to do the math here. We just want to take a look to see and conceptualize this, and then I'll show you the math. Okay, so it says we've got this reaction, aluminum solid, manganese, aluminum, manganese, and then we've got our E cell value. And this standard, again, means that we are under standard conditions, standard like room temperature, for example, it would be 298 Kelvin, and this is really important, 1 molar concentrations of everything. That's really important, that if it's standard conditions, then it's 1 molar, okay? Now, if I were to write my K or my Q for this reaction, then this is important. Remember that you do not include solids and liquids. Only gases and aqueous would be included. So if I did want to write what my Q would be for this reaction, my product is aluminum 3+, raised to the second power divided by my Mn2 plus raised to the third power, okay? So that's it, because then my solids are not actually included in my expression. The voltage of 0.48 is true if the standard cell conditions, like we said, are 1 molar and 298 Kelvin. What is the cell voltage if instead we change the concentration of the Mn2 plus to 0.5 and the aluminum to 1.5? In other words, I'm going to increase my concentration. Instead of being 1 molar, my aluminum concentration is going to go up to a 1.5 molar. So this is going to go to a 1.5 molar, and my Mn concentration is going to go down. From 1 molar, it's going to go down to a 0.50 molar. Well, similar to Le Chatelier's principle, if you have too much on your product side, your reaction is actually going to want to reverse. It's going to want to go backwards. So again, this is really important. I kind of wrote a little bit of a side note down here, and I said for Q versus K, you're not using the actual value of K. Rather, we're going to assume 1 molar concentrations for the solutions, and so K is equal to 1. So you're not actually comparing it to a K value that's not equal to 1. So I wanted to make sure that I explained that, because products over reactants would be 1, in this case, 1 squared over 1 cubed, which is just going to be equal to 1. So we want to actually compare it to 1. Okay. All right. So in this case here, the question is asking me, what should be happening to my voltage? All right. Well, if I have too much on my product side and I'm going to be reversing my reaction and going to my reactants, then my voltage should actually go down. But the question is by how much? And I want you to see what happens with the math, and this is pretty quick just to kind of get an idea. So we know it was at 0.48 volts. So let's use our Nernst equation here, and you can see I plugged in my E cell values here. My 0.48 was my standard, minus 0.0592 over my moles of electrons, which was 6 moles of electrons was being transferred. And if you want to take a look at why was it 6 moles of electrons, because my Mn is going from a 2 to a 0, which is 2 electrons, but you have to multiply by 3, so that's 6 electrons. My aluminum is going from a 0 to a 3, which is 3 electrons, but multiplied by 2, that's 6 electrons. So when it's balanced, it is 6 moles of electrons. And then the log, in this case, if I do the math, I actually get 18. So how do we get 18? Let's plug in our values here to see how we got 18. So all we have to do is 1.5 squared divided by 0.5 cubed, and when I plug that into my calculator, I get 18. And so that's where we get the 18 from. When you end up doing all of this math, you end up subtracting and you get that the voltage is 0.47 volts. It was 0.48 before. It didn't go down by that much, but again, what was important was that since we were favoring the reactants and our reaction was going backwards, that our voltage should also be decreasing. So the voltage should decrease. If we favor the reactants, then K is going down, K is decreasing, so our E cell should be decreasing as well. All right, and the last question on here, question 7, we've got another equation here, and it's saying they're giving us the concentrations. What should happen to the E cell voltage and why? Remember, E is for 1 molar solution, so calculate Q, and then let's predict the direction of it. All right, so go ahead and try this out, and then I will show you how to work this out. Okay, so I've calculated Q, which hopefully you were able to use the numbers here to figure this out. The only ones, don't forget, that you're not including are the liquid and the solid in your expression, so hopefully you did that correctly. And so when we calculate it, we get 4 times 10 to the negative 5. Remember, this is our Q, and we have to compare Q to K, and we're actually calling K 1. So if that's the case, Q is less than K, because 4 times 10 to the negative 5 is less than 1, which means we actually need to move forward towards the products. So we're going to actually favor the products, and if we favor the products, that means that K should increase, and if K increases, then our E cell should also be increasing. All right, so let's actually do the calculation. If you want to try it out and see how you do, let's go ahead and plug this in, and then we can get an idea of what it would look like mathematically and how much our E cell is actually going to increase by. Okay, so I've done this calculation, and I plugged in my E cell that they gave me originally as 1.76 volts, and then I worked out the math for this, And then we plugged in the natural log of the 4 times 10 to the negative 5, which is my Q. So this here was my Q value that we found. And after doing all the math, I get 1.89 volts. Look at this. It's not that much different. It definitely went up, but not by that much. And so that was the issue with them, and why I think that the College Board decided to actually remove the equation. Again, they're putting it back on, so I'm not sure what, what the rationale was, but the idea was that people were losing sight. They were getting so caught up in the math, and they were losing sight of the conceptual idea of it. And so you always want to make sure that you don't do that. Get your idea down first, and then sometimes you don't even need to do all the math. You can really just give a nice estimate for the answer. I hope this was helpful, and I wish all of you a happy day.